Hello friends, I welcome you in lecture number 11 on group theory. In this lecture we are going to discuss one more problem on group. So we start with this example. Show that the algebraic structure G with star is a group where G is given by set of all ordered pairs AB where A and B are real numbers and first component of this ordered pair is non-zero, and star is a binary operation defined by ordered pair AB star CD equal to AC, BC plus D, that is first component of resulting ordered pair is product of first components of both the pairs, that is first component of first pair into first component of second pair, and this is obtained by second component of first pair multiplied with first component of second pair plus second component of second pair. So in this way this is the operation given. For example, if we consider 2 3 and say 1 5, then this is going to be first component into first component, that is 2 into 1, then B into C, that is second component into first component, so 3 into 1 plus D, which is 5 here. So this is equal to 2, 8. So this is the way how given operation is defined, and we have to prove that given set G is a group with respect to this binary operation. So we are already given that G is a group. We have to prove that all the properties are satisfied. Okay, whenever we have this type of questions, show that G is a group, that means it is already known that our set is a group under given operation. We just have to prove that all the properties are satisfied. So first we start with first property, closure property. We have to show that this star is a binary operation on G. So for that we start by taking any two elements in G for any AB, CD, or we can write in this way. We take arbitrary elements in G. Let AB and CD be two elements in G. Now the elements of G are ordered pair AB such that A and B are real numbers and first component is non-zero. So because AB and CD we have taken from G, we have this A, B, C, D all are real numbers, and this A is the first component of first pair, it is non-zero, and C is the first component of second pair, which is also non-zero. Now we have to show that AB star CD, that is this one, AC and BC plus D is also in G. So this is in G if these two components are real numbers and first component is non-zero. Now all these ABCD are real numbers, so therefore it is clear that A into C is also a real number and B into C plus D is also a real number. So therefore we can write that AC and BC plus D belongs to R, and because A and C are non-zero, their product is also non-zero. So A into C is non-zero. So therefore ordered pair AC, BC plus D is an element of G because first component is non-zero and both the components are real numbers. So we had started by taking arbitrary elements in G, and we find that there whatever element we obtain by applying this star operation to these two elements, that element is also in G. So for any two elements A, B, C, D in G, AB star CD is also in G. That shows that star is a binary operation on G. So first property is satisfied. Star is a binary operation on G, or we can write that G is closed under star, or okay, so both are the same statements. Star is a binary operation on G, or G is closed under the operation star. Now we check second property, that is associative property. So for that we have to consider three ordered pairs. Suppose AB, CD, EF be any three elements in G. Then we have to show that AB star CD star EF, and if we can combine CD and EF, then they must be same. So this we have to prove. So here I can write that to prove that AB star CD star EF equal to AB star CD star EF. So one way is we can first find out this quantity. We will give it number 1 whatever we obtain, and then we will find out this quantity and we will check whether both the quantities are same or not. So first we start from this AB star CD star EF. So first we apply the definition of given operation to these two pairs. So by the definition of binary operation, it is AC comma B into C plus D star EF. Now again we apply the definition of binary operation star to these two elements, and we recall that binary operation is AB star CD equal to first component into first component, second component into first component plus second component. So using this definition, here we will have AC into E, that is first component into first component, comma second component into first component, that is BC plus D into E, and plus we have to add this second component. So now we can simplify this. This we can rewrite, we keep this as it is, and here we can rewrite this as BC into E plus D into E plus F, and we give this number 1. If required we will modify this, but for the time being we give this number 1. Now we find out this quantity. We combine CD and EF. So AB star CD star EF. So this is equal to AB star. First we find out this quantity using the definition of binary operation. We will have first component into first component, that is C into E, then second component into first component, which is D into E plus second component. Again we apply the definition of binary operation. First component, which is A, into first component of second, which is C into E. Similarly, second component into first component, which is B into CE plus second component, which is DE plus F. Now let us compare this with quantity which is written in 1. In 1, first component is order pair, not order pair, it is AC into E. So here we have A into CE, but we know that all these are real numbers, so we can rewrite A into CE as AC into E. Now this quantity is BC into E, so we can rewrite this as BC into E using the associative property of real numbers, and we keep this as it is, and we give this number 2, and we find that AC into E, which is here, and BC into E plus DE plus F. So 1 and 2 are equal. Right hand side of 1 and 2 are equal. That means we can write that from 1 and 2, we find that AB star CD star EF equal to AB star CD star EF. So this shows that the operation star is associative, or associative property is satisfied. ASSOCIATI, associative on G. So this property is also satisfied. Now the next property is we have to check what is the identity element. So now we don't know what will be the identity element in this set G. So we can assume that we assume some ordered pair. Suppose we consider, say, PQ be an identity. So if PQ is the identity, then by the definition of identity, if we consider EB star PQ or PQ star AB, then we must have order pair AB, and this must be true for any AB in G. So our aim is to identify this order pair PQ, which values of P and Q will work so that PQ is the identity. So we first try to solve this equation AB star PQ equal to AB. We try to solve this for P and Q. So this implies, if we apply the definition of binary operation, we have first component into first component, second component into first component plus second component. This is equal to AB, and we know that if two ordered pairs are equal, then corresponding components must be equal. So AP must be equal to A, and this B into P plus Q must be equal to B. This gives me P equal to A by A. Now this order pair AB is an element of G, so therefore A is non-zero. So we can cancel out A, because AB is an element of G, and element of G has this property, first component must be non-zero. So I can cancel out A because A is non-zero, and I obtain that P equal to 1, and I can put P equal to 1 here. So if I put P equal to 1, I will have B plus Q equal to B. Therefore Q equal to B minus B, which is 0. So therefore we find that PQ equal to 1, 0 is the identity element, is the identity in G with respect to the given binary operation. Now if you wish, you can write in this way also. If you don't want to write in this way, then first you try to find out which element will work as identity, and then you can write in this way: for any ordered pair AB in G, we can show that AB star 1 0 equal to AB. So this is equal to first element into first element, second element into first element plus second element by the definition of binary operation. Now A into 1 is A, B into 1 is B. And similarly we can show that 1 0 star AB, this is also equal to 1 into A, then second element into first element, which is 0 into A plus B. Now 1 into A is A, 0 into A is 0 plus B, which is AB. So therefore for any element AB in G, we find that AB star 1 0 equal to 1 0 star AB equal to AB for any ordered pair AB in G. So therefore we can say that 1 0 is the identity of G or identity in G. So existence of identity is also proved. We find that order pair 1 0 will work as identity element. And the last property is we have to show that every element of G has inverse in G. So for that we start by taking any element in G, and we have to show that this element has inverse in G. So for that we assume that some ordered pair is inverse of this element. Suppose that say RS is an inverse of G. So if RS is an inverse of G, then by the definition of inverse, AB star RS equal to RS star AB must be equal to identity, which we have shown that it is 1 0. So now we have to solve this equation for this R and S. Our unknown quantity is order pair RS. So we try to solve this for RS. So this implies A into R, that is first element into first element, then second element into first element plus S equal to 1 0. This is by the definition of given binary operation. This implies A into R equal to 1, B into R plus S equal to 0. This gives me R equal to 1 by A, and because AB is an element of G, we have A is non-zero. So this is meaningful. We can divide by A because A is non-zero. And if we put R equal to 1 by A here, we have B by A plus S equal to 0. Therefore S equal to minus B by A. So this element 1 by A comma minus B by A is an inverse of order pair AB in G, and because of this order pair AB is an element of G, A is non-zero, so this is meaningful. We can divide by A. Or another way of writing this is, first we can find out by doing this procedure that which candidate will be an inverse. So here we find that 1 by A minus B by A is an inverse. So we can write in this way also: for any AB belongs to G, we write that AB star, the element which we have obtained is 1 by A comma minus B by A. So this is equal to, by the definition, first component into first component then second component into first component, which is b by a, plus second component, which is minus b by a. And here a is non-zero due to this, because ab is in G, therefore a is non-zero, so we can cancel out a here, and this is going to be 0. So we obtain identity element, as well as we have to write this part also, 1 by a minus b by a star ab equal to first component into first component, that is 1 by a into a, then second component into first component, which is a here, plus second component. Now because a is non-zero, this is 1, here we will have a will cancel out, so we will have minus b plus b, which is 0. So therefore we proved that 1 by a minus b by a is an inverse of element ab in G. So because this is arbitrary element, every element of G has an inverse in G. So these are different ways of writing the same property. If you wish, you can write in this way, and if you are not comfortable, you carry out this procedure of finding the inverse, and then you can write in this way, which I have written here. So all the properties are satisfied for a group, therefore we can say that G with given binary operation is a group. So this is very easy problem. You just have to take care that how your operation is defined. So we are asked to prove that this G with star is a group, and we have shown that all the properties are satisfied. Therefore G is a group under the given binary operation. So this is all about this lecture. I hope you like it. Thank you very much.